All right, we got one last video about manipulating Taylor series to generate Taylor series for other things. We've done composition, we've done addition and subtraction, we've done multiplication and division. Now I want to do differentiation and integration. So I've got a couple theorems here. The first one says that if I've got a function and it's Taylor series, then the derivative of the function, the Taylor series for the derivative of the function is just, you just take the derivative of the Taylor series, right? So the a to the n, x minus b to the n is going to come out in front, times that constant x minus b to the n minus 1 power, times the derivative of the inside, which is 1. Right? So just take the derivative like it's a big old polynomial. Likewise, if you want to integrate a function, the antiderivative of a function is just the antiderivative of the Taylor series. You can just, term by term, like it's a polynomial, take the antiderivative. So bump the exponent up by 1, divide by the new exponent. Right? And neither operation changes the interval of convergence. So whatever the interval of convergence for the Taylor series for the function was, that's the interval of convergence for the Taylor series for the derivative, and likewise for the antiderivative. Okay. So let's do a couple of examples here. First one, we'll do the arctan. I noticed that the derivative of the arctan is 1 over 1 plus x squared. And in a previous video, the first one I think, the first one about section 5 here, that the 1 over 1 plus x squared, the Taylor series is 1 minus x squared plus x to the 4th minus x to the 6th, and so on. And so the derivative of the arctangent is this thing, so the arctangent is the integral of this. I should probably have a dx in there, which I don't, but anyway, I'm replacing this thing with its Taylor series, and then I'm going to integrate term by term. So the arctan is, when you integrate the 1, you get the x. X squared is going to go into an x cubed over 3, and x to the 4th is going to turn into x to the 5 over 5, and then an x to the 7 over 7, and there's alternating signs here, so there's still alternating signs down here. So the Taylor series, or Maclaurin series here, for the arctan is x minus x cubed over 3, plus x to the 5th over 5, and so on. I do notice that the arctan is an odd function, and it uses only all odd powers here. The interval of convergence of this original one was from minus 1 to 1, and so the interval of convergence for the arctan is also for x between minus 1 and 1. And there's an interesting point here. I haven't looked at any endpoints. I've really ignored what's going on at the endpoints of these intervals. It does turn out that for x equals negative 1, this does converge. That if you look at what happens at the endpoint here, plugging I have this wrong. Shoot. This should be a less than, and this should be less than or equal to. I'm plugging in the positive one here because it's already alternating signs here. So anyway, this should be a greater than or equal to on the one, but just a greater than on the other one. So anyway, plugging a 1 in, I've got a 1 minus a 3rd plus a 5th minus a 7th. This is an alternating summation. Each term is getting smaller and smaller each time, with the limit being 0 on that. And so there's a theorem that beyond the scope of this course that says this has to converge. And it turns out that it converges to the arctan of 1, which is pi over 4. So this is a way of calculating pi. For instance, if you multiply both sides by 4, so I had 4 minus 4/3 plus 4/5, you could just keep figuring out each of those fractions and adding or subtracting them on. In fact, I think next Pi Day I might try this with a bunch of people to see if we can calculate pi using this method. Let's do one more example. 1 over 1 minus x is interesting in both directions because you can integrate it to get a natural log of maybe we would want to have a plus there, but anyway, both directions, integral and derivative, are interesting. Let's do the derivative for this one though. The derivative of this thing, you can think of it as 1 minus x raised to the negative 1 power. So you'd have negative 1 minus x to the negative 2 power, then times the derivative of the inside, which is negative 1, and the negative turn out to be positive. So this just turns out to be 1 over 1 minus x quantity squared. And so I can get the Taylor polynomial for this 1 over 1 minus x quantity squared by taking the derivative of that thing, right? And I can just take the derivative of the Taylor series term by term. So the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, the derivative of x to the fourth is 4x cubed, and then 5x to the fourth, and so on. Right? And so without having to take derivatives of this thing and plugging in x equals 0, I could just take the derivative of the Taylor polynomial that I already had to get the Taylor polynomial, the derivative. Of course, the interval of convergence of the original one was -1 to 1, so the interval of convergence of this new one is also 1 to 1, -1 to 1. I will point out it's not immediately obvious that that's true, because where the original is a geometric series where each time you multiply by the same thing to get to the next term, right? Multiplying by x each time. Here it's not. If you just multiply the 3x squared by x, you would get 3x cubed, but you have 4x cubed. So, and it's not even like, oh, I just multiplied by 4/3. Well, if you multiply 4 by 4/3, you don't get 5, right? You had to multiply by 5/4. So you're multiplying by a different thing each time. This is not a geometric series anymore, but yet it's close enough to a geometric series that it still converges in that same -1 to 1 range. Right? So there you go. That is the last thing we're going to do in this course for new material. Thanks for watching.